Being you guys are on a tight schedule, I'll go ahead and get started. Good morning, everyone. My name is Roger Fritz. I'm the head of AC-DC-HOTLINE and also the Nikola Tesla Group. And I've been in the motor industry for about 40 some years. And what we're going to talk about today is basically clean power and what it does to motors, and also introduction into the Smart D technology, which is a more of a pure sine wave output and a pure sine wave input type device for variable frequency. You're welcome to join today, the Nikola Tesla group. I put it in the chat. If you have questions as we go forward here, you're more than welcome to, ask those questions, put them there, and we will address them, shortly. Um, I always introduce just briefly with, this this little video about Tesla.
When you think of electricity, you think of Edison. But there is one electrical genius who is nearly forgotten. A man who dreamed of giving the world an unlimited supply of energy. His name was Nikola Tesla. This is the story of a modern Prometheus who changed the world with electricity. It was Nikola Tesla who captured the power of Niagara Falls with his alternating current system and made it possible to transmit electricity to all of America and the world. Suddenly knew he could recreate this rotating field by powering the coils of a motor in different steps or phases, like the pistons of an engine. The resulting forces of magnetic attraction and repulsion would literally twist the rotor in a circle, the electrical equivalent of the wheel. And all this was accomplished with alternating currents.
And the reason I bring this up is because, as you saw in the video there, that there was a pure sine wave that was fed to these original induction motor designs that he had. It wasn't for square waves. The IGBT transistor puts a lot of pulse out. And so I'm going to go ahead and move on forward. We have several videos available of difference in noise level, heating, and those things in the opportunity. I'd like to introduce to you Simon this morning. I'm going to let him do a screen share, and he's going to talk about the Smart D drive technology that they've have developed, and is in the market, and it is extremely useful. So I want to get that available to you. So I'm going to go ahead and let you share, Simon, and I'm going to stop my screen share.
Okay, can everyone see my screen?
Yeah, I can. Go ahead.
Perfect, great.
Yep,
So
you got it.
let's get going. I know everyone here actually knows about VFDs, but just as a reminder, the growth we've seen in the market is, of course, driven by some control requirements. So process is driving the adoption of drives, so we control the speed. But the big driver has been energy consumption. So laws of affinity enabling large saving when we reduce the speed of loads, specifically variable loads. And then, one of the third pillars of what is touted as a big benefit of VFD is the enhanced system reliability. So reducing mechanical stress, namely on the motor. But that's kind of ironic, actually, because drive also come with large and significant disadvantage. They generate a lot of harmonics on the grid, and I think with the rise in renewable, this is becoming more and more. There's more and more attention there, but contrary to the reduced mechanical stress that drives bring, they also bring a lot of electrical stresses. So they do have some issues, or bring some issues on the motor side through their pulse width modulation, or PWM. So really at SmartD, our goal is to bring a drive that don't have those drawbacks, a drive that is filterless, that is sine wave in, sine wave out. And that has been our target since our inception in 2018. So, and we continue to increase our catalog as we go through this. Our agenda for today will be pretty straightforward. I should have about 25 to 35 minutes of presentation. We are a small group, so don't hesitate to stop me if you have questions. And then we will follow that up with a question period. We'll go first through harmonics, so issues on the grid, and then PWM, so issues on the motor. We'll deep dive into our technology. Then we'll have a quick overlook of our product and what to look for in the market to fit that product. So, as I go through the presentation, you're going to see I'm going to talk about the theory. What do drives do today? How that compares with actual lab results done by a third party. This is a dedicated power electronics lab with a very large transformer and long cable, so we have kind of extreme conditions to compare. And then we'll, in each case, look at field results. What do we see in the field, and how does that translate for potential opportunities for you? Let's get going and start on the grid side with the impact of VFDs on harmonics. To understand how VFD generate harmonics, we need to look at the architecture of a VFD. And I'm sure you're all familiar with it, but just as a reminder, there's three parts really: the diode bridge rectifier, the DC bus, and the inverter with silicon IGBTs. And harmonics on the grid really take their source in the diode bridge rectifier. The goal of the rectifier is to really transform the AC signal into a DC signal. And it does that by only enabling passing of the signal when the voltage is high enough to charge the DC bus. And you can see it creates this kind of hump-like voltage signal. And in between each of these hump, actually no current is drawn on the grid. And so it's this lack of symmetry between the voltage waveform and the current waveform, which makes it a nonlinear load, and which causes harmonics on the grid. Typically, a drive with a diode bridge will generate between 30 and 50% harmonics. And of course, that makes it non-compliant to standard, but for your users, the main consequence of harmonics is heat. So the percentage of harmonic you're sending to your equipment is basically energy that can't be used, and that needs to be dissipated as heat. So if you have 40% harmonic, you're probably going to have to oversize your UPS, your generator, or your transformer by 40% to be able to handle that extra power and that extra heat. Harmonics can also have other consequences, such as creating interference with other electrical equipment, but really heat is the main consequence. Typically, to deal with those harmonics, you will install a line reactor or a harmonic filter. And if we compare and go to the lab and check, how do the SmartD drive compared to a 6-pulse drive compared to a 6-pulse plus the passive harmonic filter? Well, we can first visually see on the screen the standard drive connected to the grid without anything is in the middle. And you can really see visually that you don't have a equal signal in voltage and current. Actually, you can see the nonlinear draw from the current waveform. Introducing a passive harmonic filter at the bottom of the screen actually corrects that, and you can see you now have sine waves that looks much closer between the voltage and the current. And you can see at the top that the SmartD drive does this. So pretty much a similar impact as the harmonic filter, but without any filtering between it and the grid. You can also see the impact on the power factor. I mean, generally speaking, a drive does have a good power factor, so you're correcting and bringing it to 94, 95%. But the Smart D drive really brings that one step higher by having almost unity power factor. So you're above 99%, close to 100% power factor. And in terms of actual harmonic performance, you can see your standard drive between the 25 and 35% benchmark. And you can see that both the passive harmonic filter and the Smart D drive will bring you below that 5% threshold at full load. Now, the harmonic distortion and current is what you care for because that's what's impacting your equipment in terms of heat dissipation and oversizing. But the utility actually cares about voltage harmonic distortion because that's what is going to impact other equipment out there, and it will go beyond your own network. So in this case, you can see that the Smart D drive in green outperforms even the passive harmonic filter throughout the motor load. Now that's with a standard 6-pulse drive. There are other drive architectures out there that already natively address harmonics. So you've got your multi-pulse drives, 12, 18, 24 pulse, which will do a very good job at reducing those lower order harmonics. They do have a tendency to require custom builds and are quite bulky and expensive. And so you've seen in recent years, in the past 10 years, you've seen a rise in dedicated low harmonic drives. So either active front end drive or AC to AC matrix drives. Both of these have their own disadvantage. Active front end drive have a tendency to hide higher order harmonics that are built higher than the 50th order because they're generally not looked at. So because of the way standards are built today, people will only look at the first 50 order. And so the switching frequency of these active front end will mean that you have these peaks at higher order that are not even measured when you're reporting your THDI. In comparison, the Smart D, which you can see on the bottom screen, really does not have any of these higher order harmonic hidden. And so you're compliant even when future revision of these standards will come out and consider these higher order harmonics. So that's for active front end. The AC to AC matrix drives does not have a DC bus. So one thing is that when it is at full speed and bypass, it has very high efficiency, which is a great thing. But in any other case, it also is limited in voltage output because it does not have that DC bus. It cannot boost the voltage, and so you're going to be limited to 85% of your input voltage to go out of your drive. Because you don't have a DC bus, you're also going to be you won't have any kind of buffer between your grid and your motor. So any disturbance happening on the grid will be propagated to the motor. In any case, in all these solutions, whether multi-pulse drive, active front end, or matrix architecture, all of these still have a PWM output to the motor. So you're still impacting the motor in the same way. And kind of a glimpse of what's to come in the next section, this is the same screen capture that we had with the active front end on the grid, but now we're taking that same screen capture on the motor side. And you can see that you have lots of harmonics all across the board compared to Smart D, where you have really clean signal. But and illustrating that, into the field. You can see here where we've done a deployment at a data center and took advantage of the fact that there was a requirement for a choke on the motor side. And with our drive, we were able to eliminate that choke, reduce the panel size, and reduce the overall cost for the user. So very good example where you have a harmonic requirement, we meet that, and we eliminate anything else required around it. So it makes for a very, very clean and simple panel. With that, let's change side and go on the motor and understand what pulse width modulation exactly does to those motors. Now, as much as harmonics on the grid were caused by the diode bridge, the pulse width modulation is the desired output of the inverter side of your drive. Basically, after having this hump signal by the diode bridge, then flatten out in the DC bus, you have a DC signal that you need to retransform into an AC signal. You do that by having these high-speed pulses, typically 2 kilohertz. And these high-speed pulses, by controlling the duration of each of them, you're creating a quasi signal, a quasi sinus in current, and you can see it in this representation. But as you've seen in the previous graph, this generates a lot of harmonics, and these harmonics will have the same impact on the motor as they do from the on the grid side. Is the first consequence is overheating. So your motor will heat more than if it was fed through a contactor. The other consequences will be sound level and vibration. Those are the 3 ways that those harmonics will be dissipated. If you really wanted to avoid that temperature shift and reduce that sound level, you'd have to go to a sine wave filter. Not saying that you'd actually put a sinusoidal filter just for the sound or temperature, but that's really the only way to get around it. And you can kind of see it here visually as we compare the lab results of our drive, the standard 6-pulse, in that 6-pulse with a sine wave filter. You can see how you've got the PWM in the middle, so you clearly see that square signal translated into this kind of jag sinus current signal. And the sine wave filter is really correcting that. So this is coming out of the drive, and then it's transformed into this nice signal at the top by the sine wave filter. And same thing on the current here, which is kind of jagged coming out of the drive, and then smoothened out by the filter. In the case of Smart D, there is no filter, and you can just see how you've got directly clean sine wave signals out of the box. The consequence of that is if you measure the temperature of the motor, you've got about a 10% temperature difference between a drive that is driven by a Smart D drive and a motor that's driven by a Smart D drive and a motor that's driven by a standard 6-pulse drive. That translates into motor longevity, as temperature is one of the leading factor causing degradation of motors over time. Now, if we look in the field, we can actually observe that also in the field, this time through the sound level. So you can see this is a pumping station where we had 2 pumps side by side, one driven by Smart D and one driven by a standard 6-pulse drive. You can see the difference in signal, and you can see the difference in sound. So you're talking over 15 dB difference in sound. And actually, that's something that very often a customer will tell us as they first install in Smart D. They're going to call us and ask us, is there a problem with your drive? I can't hear my motor. It's probably not running properly. Well, that's really the result of not having those harmonics going to the motor. That being said, It's not because we don't have harmonics that we don't have energy savings. We did deliver there your expected energy saving from a drive retrofit. So going from a contactor to a drive, I think they achieved 35% energy savings. Second consequence of a drive on the motor side is the voltage spikes. So as you have these PWM going out of the inverter, each one of them has this spike at the rising edge of the signal. And the spike in itself, goes above the intended voltage or desired voltage, but it gets worse the longer your cable. And this is where, as you hit the motor, you've got a reflection of your wave, which can then combine with an incoming wave and increases the amplitude. So this is why the longer your cable, the more you can have an issue with your voltage, and you risk exceeding the motor insulation and exceeding the cable insulation. So this is why you're going to typically see a recommendation to have an inverter duty motor when you're using a VFD, so that they can sustain that extra those voltage spikes, and special VFD cable, especially if you have longer cable length. And a lot of the time also either a choke, a DVDT filter, or again, a sine wave filter, depending on the length of the cable. We can see here lab results once again between our drive and a standard drive. You can see in pink the standard drive. This is at 480 volt with 500 feet of cable. You can see how you can get up to 1800 volt voltage spikes because of those long cables. And on contrary, whether you're putting a sine wave filter or the Smart D drive, you're able to maintain that signal very flat and eliminate all of your voltage peaks. So this is comparing, again, the Clean Power VFD connected directly to the motor, no filter, to a 4.5 kilometer rated sine wave filter. So in both cases, you're really maintaining that signal nice and clean. And you could always challenge me and say, hey, Simon, why is that green line above the blue line? Doesn't that mean that the sine wave filter is more efficient at avoiding motor peak voltage? Well, actually, a sine wave filter is a big chunk of metal, and so putting that necessarily induces a voltage drop, which means that your peaks will be lower. So it's not necessarily a desirable outcome, because with long cables, you don't want that voltage drop. It's just the reality of putting that big filter at the output of your VFD. Again, if we translate that into the field, this is retrofit we did in Ontario, Canada, where they had an existing submersible pump. It was on a contactor. They tried replacing it with another VFD, and that failed because of the cables, because maybe of their degraded nature. They had tried with filters, but anyways, they had to take it out. It did not work. And it stayed that way for quite a few years until they heard about us. And here we were able to install this Smart D drive, as is, again, no filter. And with the pure sine wave output, the 1300 feet cables were not a problem. They were able to go get those energy savings by reducing the speed, which before the flow was constrained through a valve. So not only were they not getting energy savings, but they were just increasing the pressure out there through that valve. So double demonstration here, compatibility with long cables and compatibility also with existing equipment, both an old submersible pump and old standard cable. Third and final consequence of VFD is common mode noise. And common mode noise is created by the fact that you don't have three sinusoidal signal coming out of your drive. If you did have three perfectly balanced sinuses outside of the drive, the sum of these would always add up to zero. But in this case, you can see that your pulses don't add up perfectly. And so you have this leftover voltage known as common mode voltage. And this can be quite high, it can be above 100 volt. And so you're sending this common mode voltage into your motor, where you're inducing a shaft voltage, which then induces bearing currents. And so you've got this current circulating in your motor, trying to get out. And to get out of the motor, the easiest point is through the bearings. And it's this ongoing arcing that's happening in the bearing that will cause pitting, frosting, and flooding of the bearings, and eventually the failure of your motor. So again, you need to rely on mitigation. So whether it's insulated bearings, shaft grounding rings, or common mode chokes, in all cases, you're not really addressing the root cause of the common mode. You're trying to get that common mode to go elsewhere. And if you look at it, we've got a good example here where in the lab, we can measure that this is the level in pink of your standard drive common mode current, so the result of your common mode voltage. And by putting a sine wave filter, of course, that's not the main objective of the sine wave filter, but you are reducing it somewhat because some of it is actually going through this other structure that is the sine wave filter. But it's the same principle when you're putting other equipment. You're just trying to redirect that current to flow elsewhere than the bearings. But in our case, we're eliminating 95% of that common mode current. And so we can't say we have zero, but you're really addressing the root cause of your issues and reducing it to a minimum. And again, we can go into the field to see how we've addressed this. This customer that came to us to address a ongoing issue they had with bearing failures that were happening every year. They had already installed filters on the motor side. They had already replaced the motor and tried if that was addressing it, but to no avail, kept on having the issue. So they installed the Smart D drive, and the interesting thing is they were working with a specialized firm to monitor the motors through vibration analysis, and they had identified the problem through that analysis. And afterwards, when they went after the Smart D drive was installed, they could measure that there was a reduction of up to 95% in vibration acceleration and nearly up to 90% in reduction in spike energy. So really significant reduction in the vibrations and the impact on the bearings. And more importantly, no change in the bearings since the install of the Smart D drive. For this next section, we'll deep dive into what is the technology behind our drives. And at the core of it is silicon carbide. So I've mentioned IGBTs quite a few times. Those are transistors, silicon-based transistors. Actually, IGBT stands for insulated gate bipolar transistors. They've really been the heart of VFDs since the 1980s, and they've enabled the rise of them by making them simpler and more resilient than what was there before. So IGBTs really fueling those drives since the 1980s. Silicon carbide introduced in labs probably 15 years ago, but really as a commercial and industrial product 6 or 7 years ago when Tesla announced that they would now use silicon carbide in their Tesla 3. And so that really changed the game. silicon carbide was now in the prime time and increase the output, availability, robustness, and so on of this material. But why were people interested in it in the first place? Well, it has a number of characteristics that makes it very interesting in power electronics and specifically power conversion applications. First, it can switch much faster than your typical silicon-based transistors. So, a typical drive will be around 2 kilohertz. In this case, we can switch it at above 100 kilohertz with no major impact. It has a higher power density than silicon. Because of the higher switching frequency, it can reduce the passive component size. It reduces the converter loss. So for the same switching frequency, it has about 10 times less losses in both switching and also conduction. And so because of that, you're generating less heat. Finally, we do need to be wary that you can't just introduce silicon carbide in a traditional IGBT-based architecture. If that was the case, I'd say all the manufacturers would have switched over already as of today. But if you do that and you just put your silicon carbide and put it in existing architecture, you're going to have more EMI. And so you're not going to be compliant to a lot of standards, namely in Europe. Now, the other thing is also on the motor side, because of the fast switching that's happening, your DVDT issue is going to actually just get worse. So you really need to address these two things and can't use it as is in an existing architecture. So what we do as Smart D is we do have an active front end drive, but we are using silicon carbide MOSFET to switch at a much higher frequency. So typically above 100 kilohertz. We're also using a 3-level architecture instead of a 2-level architecture that reduces the voltage steps. And then we use advanced modulation techniques to cancel harmonic cluster directly through mathematics. When we combine all of these three things together, we're able to miniaturize filters, reduce them by a factor of 200, and integrate them directly in the drive. Now, as I mentioned, we do need to be wary about EMI because the faster switching does generate more noise. And so to address that, we're integrating into our active front end design not only your standard LC filter that will address harmonics, but we're doubling that as an EMI filter at the same time. And with that, we're able to reduce by 70 dB in differential mode and 80 dB in common mode the EMI noise. So with that, you can see that you can really put our drive directly on the grid. You don't need to have any kind of harmonic filtering between it and the grid. Now let's continue and look on the motor side where we take a very similar approach. So we have our multi-level architecture, reducing those steps in PWM amplitude. We integrate a filter here, but it's an output filter instead of being an LC filter. With it, instead of having garbage after long cables, which really would be the result of your DVDT with silicon carbide, because we have this integrated filter, we have a sine wave at the output of drive, and we have a sine wave even after super long cables. So with that, you save any and all kind of mitigation that you'd have at the output of your drive. So no sine wave filter, no DVDT filter, or inverter duty motors or inverter duty cables. You can have standard motor and standard cable. So very easy retrofit without any kind of filtering. And you don't need mitigation for common mode noise. So no common mode choke, no insulated bearing, no shaft grounding ring. You can just go with your standard bearings and you're good to go. I really like this slide because it does gives a really good simplification. Before, as you were looking at installing a VFD, you instantly had to think about mitigation. How do I avoid all of these issues and pitfalls I've talked about today? And with Smart D, you're really talking about simplification. You put your drive and you don't think about the harmonic filters, the common mode choke, and so on and so on. And necessarily, you're reducing the footprint that you need because you don't have those other equipments, and you're not causing your typical failures that are seen with VFDs. Last thing to mention is that the Smart D Clean Power VFD is a 4-quadrant drive, so fully regenerative, able to get flow back to the grid if you're breaking in any way, shape, or form. Final section of our presentation today before I open the floor to question. Our drive is very similar to other drives out there on the market. A few things to point out. So we do have a touch HMI, which enables us to roll out features much more easily. We do have an upgradable drive, so you can, in a few minutes, upgrade the firmware on it. And if you have new features coming out, well, you get a new screen, and we don't have to mess around with buttons and sequence of buttons. So it makes for a very user-friendly and intuitive interface to work with. It is also a multilingual interface. So today we support French and English, but there's definitely the opportunity to translate with other languages as we have partners in new countries. In terms of I/O, I'd say it is pretty rich as drives go. So it's maybe a standard I/O profile for an industrial drive with relay, STO, analog output, power input, digital inputs. You can have an auxiliary 24-volt in. So that means even if the main line would lose power, you could still access your drive and get access to the log or update the firmware. You can configure the drive also without having the main line on, which is quite appreciated by some of our partners, and so on. Finally, our drive also has integrated industrial protocols. So today it supports Modbus TCP and BACnet IP, and we are rolling out Ethernet IP in early 2026. So you don't need any add-on cards. You have everything integrated directly in the drive. And something that not many drives have, we have native support for our mobile app. So you can do the full configuration of the drive directly from that mobile app. If you want to go and try it, it's available both on Google Play and Apple Store. And so you just need to search for the Clean Power VFD app, download it, and you can even work with it offline, so without even having a drive. And you'll see there's a very easy, intuitive, step-by-step configuration wizard you can go through. So if you do download it, make sure you give us feedback. Always welcome. So with our very unique drive, where should you be looking at? Well, anything with low harmonic is definitely of interest because we are a low harmonic drive, but it does have a tendency to be spec-based. So you do need to work with specifying engineers and the end users to make sure that you bring everyone together according to the spec. Retrofit is a place where definitely we're seeing a lot of traction. And the interesting thing about retrofits is that typically you don't have an RF. You can just go, and because of the simplicity, it can be a very transactional business. But again, remember that with retrofit, we eliminate the need for a special motor. We eliminate the need for special cable. So you can just go take out the contactor, put our drive, and you're good to go. And finally, I'd say any place where you're seeing a lot of filters being used is a place where you should be discussing Smart D because of that simplification I talked about. I said finally, but actually the finally is energy regeneration. So any application where you would be regenerating to the grid is of interest, or if you have a braking resistor, take that braking resistor out, and instead of burning that energy, feed it back to the grid, so to take advantage of that. That sums up my presentation. So you can see a good summary. As I told you, since 2018, our goal at SmartD has been to simplify drives, eliminate the constraints that come with drives today, and we come with a drive that has sine wave in, sine wave out, um, and that's really the core of it.
Thank you, Simon. We have a question for Mr. Pitko. What's the max power output available?
So today we have an 82 amp drive, which is about 45 kilowatts. That's the maximum drive that we have certified, and we have a 110 kilowatt drive upcoming as well.
For everyone else, thank you, Simon. For everyone else, feel free to join the chat here and ask your questions, or you can take, as we are a small group today, you can take the microphone and just unmute yourself. While we wait for more questions, Roger, do you feel, is there anything that you think we should address that wasn't addressed in the presentation thus far?
No, I think it was addressed very well. Thank you, Simon. One thing I think that is very important that a lot of people lose track of is what is harmonics, and really what they're doing with these PWMs and the frequencies and stuff there. That's actually creating, when you have long cable, like you're creating a radio tower. I mean, those are for high frequencies, and you can literally hear them with an AM radio. And the effects, people, a lot of people think, well, I'm going to use a soft starter. Or am I going to use a VFD? Or what I'm doing, they think a VFD is a soft starter. Well, a PWM drive is not a specific soft starter. It's got way more complexities. I've seen thousands of installations where you run into the issues of all of a sudden it's affecting my flow meter, it's affecting my circuit boards in my
Hmm.
PLCs, it's affecting my parts inside my machines. And they can't put a finger on it. And then the more and more, they implement drive controls in, all of a sudden they've got major, major problems. I've dealt with, many, many facilities, and what happens is that that noise becomes very problematic. And because with a standard amp meter, you can't see it because they only pick up 60 hertz power. So you have to go buy an expensive meter, put it on, and then all of a sudden you start tracking it down. But then you don't know what kind of grounding loops you're going to create because that noise then rolls in and induces and it picks up into little capacitors. I've seen it blow, circuit boards out on, molding machines. Um, and so, once I saw this product, I said, this has got to be addressed further. I think if this, MOSFET type, control was in there years ago, a lot of this still wouldn't be done, but everybody else is putting a Band-Aid on it. And it's not the way to go. And so I wanted to bring it forward. Like I said, if you have any questions, any information I can forward to you, I'll be glad to do that. I put that in there. And, please join into the Tesla group because it brings a lot of people out that, talk about problems and, how to solve what is out there that, can be solved, but it's got to be something you can see and address. And without the high, expensive, $7,000 fluke meter, you don't go see, you can't see where the noise and harmonics are coming from. So thank you again, Simon. Thank you again for your input today, and we appreciate your time.
Simon, you went in and answered a few questions. Do you want to share the answers for those who don't have their chat open?
Absolutely, and I was just answering Mr. Pitko, but it's going to go faster even. So yes, absolutely. Can we regenerate power? Yes, we can. So it is a four quadrant drive. So if you're braking, you can regen that to the grid without any problem, and you can go to max ampacity of the drive capability. So same capability in both regen and motoring. Mr. Pitko had two questions. Do you have C for Europe? The answer is yes. What about supply voltage level? Is 500-volt AC available? So the answer is yes. I'm kind of curious where you have 500-volt. We have two models. We have one that will be for Europe and US, so 380 and 460, and then we have a model that we use for Canada that can go well, standard 600-volt, but that will cover 500 and 525-volt. So definitely interested to understand what's the use case for 500-volt, but we do support it. And hi, Filiberto. With your SESA ID, I suppose you're from Schneider Electric. And so, yes, today we support induction motors only. That does not mean the technology does not support PMSM. It's just a question of bandwidth for our team to test it. So it will be upcoming later on.
All right, guys, maybe one more minute here to get your thoughts together and put a question in the chat. But if that's, oh, there you go, Simon.
Yes, Mesam, as Pitco had asked, we do have IEC tests for CE marking. Just for those who don't know, and we have a little bit of time, so a little bit background. There's been a lot of unifying around standards for VFD. Before, you had a completely different standard set for North America than for Europe. And so both have kind of standardized on IEC 61800-5. You have some regional deviation, but the core of it is now the same. So when you do your testing for North America, you'll do your informative reports for IEC at the same time, well, for most people, really. So Bitco, no, the price is not exactly the same as PWM. I wish. As we grow the business and we sell more and more of these drives, maybe we'll get there, but definitely we have a difference in volume. So the price is more expensive for these drives today. And you need to look at it from a system perspective. That's why I was telling you, look at where you have these filters being used. Look at where you have these problems, because as you add filters, yes, then the price definitely becomes competitive. But if you just look at a standard PWM drive and us side by side, then we are more expensive. So yes, we can perform vector. The question is, can we perform vector control? The answer is yes. We can do vector control both closed and open loop. So we have two of the inputs that can be connected with an encoder. So for closed loop, and we'll do vector control and both speed and torque set points.
Well, thank you so much for this, Simon. Thank you everyone for